Embeddings, a very hot topic right now, mainly because of NLP use cases. However, because that's actually the first time in weeks that we don't have any groundbreaking model that we immediately need to build a demo around, I decided to play a little bit with that idea and explore how we can use it in computer vision. First of all, we'll of course try to understand what are embeddings, but we'll also try to leverage them to look for clusters of images in our dataset, assess the overall quality of our dataset, as well as look for image duplicates. Really cool topic. I'm excited for that video. So let's dive in. Like always, we created a Jupyter notebook that you can open up in a separate tab in Google Colab and follow along. Here it is in the computer vision skills section, the first one from the top. So let's open it. This notebook can obviously be found in RoboFlow Notebooks repository, but the link is also in the description of that video. And for the first time ever, we actually created a vocabulary section at the top of the notebook. I will obviously do my best to explain everything, but in case anything is not clear, keep in mind that this section is here. We'll probably add more words to it along the way, so feel free to submit your ideas in the comments below. And let's dive in. So as usual, we start by installing additional Python packages that we will need along the way. This time we don't need the GPU. This notebook can run on a CPU just fine. And on top of that, we only need 3 Python packages, so it's pretty straightforward installation this time. So obviously we need RoboFlow because we are going to pull few data sets from RoboFlow universe. We'll use few plot utilities from SuperVision, and we are going to install UMAP. It's a scientific package that allows you to lower the amount of dimensions that you have in your data set, and we are going to use it in one of our demos. And speaking of demos, let's start the first one, and this is going to be clustering of MNIST images based on their brightness. For those unfamiliar with MNIST, it's basically a very old school computer vision dataset containing, I believe, 60,000 grayscale images of handwritten digits. And those images are very small, only 28 by 28 pixels. So given the fact that every pixel on grayscale image can be described by single int value, contrary to color images where we have 3 color channels, we only have 784 values. We can call them features that describe every single image. 784 is still a lot, so the plan is to use T-SNE and UMAP to limit the amount of dimensions to only 3 and display clusters of those images in 3D space. So let's do it. I will obviously do my best to explain everything. Hi, it's Peter from Future. I'm producing that video right now, and I kind of realized that I completely skipped the part where I was supposed to describe how T-SNE works. So let me correct that omission right now. So the whole idea is to take a data set that exists in high dimensional space, a space where we have multiple features, multiple attributes, and convert it into a data set that can live in 2 or 3D space, but preserve the similarities between individual data points. So in our case, 2 images that are very similar to each other, like for example, here is 6 and here is 6, and the handwriting style is very similar, are going to be represented by 2 points in 3D space that are going to be very close to each other. Contrary, 2 digits that are visually different, like for example, 1 and 8, are going to be represented by 2 points that are going to be far away from each other in 3D space. Okay, I hope that gives you enough intuition. Let's go back to the video. MNIST is a very popular dataset and you can find it in many places on the internet, but I'm using RoboFlow to pull it. To do it, we first need to authenticate ourselves, so I just click on the link, select the workspace, click generate token, copy the token, paste it in the Jupyter notebook, and I'm pretty much authenticated. Now we just need to wait a few seconds for the dataset to be downloaded into our Python environment. Classification datasets like that are structured using subdirectories. Every class gets a separate subdirectory, so we can just list the subdirectories in the root directory of the dataset, and we can get a list of all classes. Now we can use T-SNE to automatically detect clusters of images belonging to each of those classes, And the first step to do that is to load those images into the memory. We will load 500 images of each class and just reshape information describing those images into the format that is consumable by T-SNE, which is 2D NumPy array where every row describes a single image, and the shape of that NumPy array is n by 784. When all that processing is completed, we can just import T-SNE from sklearn and run fit method using our train dataset. One of the biggest downsides of T-SNE is actually quite slow, and for that reason we are calculating the time of execution for this method, and we will later on compare it to UMAP, an alternative solution that is significantly faster and in some cases more accurate. Okay, we don't have the whole day, let's speed up the process. Okay, the fitting is done and it took almost 90 seconds to complete. What is even more crazy is that we use only 500 images per class and the dataset contains 6,000 images per class. So if we would use all our data, it would take way longer than those 90 seconds. But enough of complaining, let's do something more interesting, which is visualization. And to do that, we will use Plotly, a Python library that uses JavaScript to create nice looking interactive charts. You have no idea how long it took me to create that chart, but the good thing is that we will reuse the template for all of our examples. Each dot on that chart represents a single image, and the color of the dot is related to the number that was written on that image. To make it a little bit easier to read, I also printed the number over the dot so we can easily see which numbers are clustered. And the coolest thing about that plot is that when I actually click the dot, I get to see the image with the number in the top left corner, which is especially useful when we see the cluster of images depicting the same digit, and suddenly in the middle of that cluster, there is one image showing different number, and we would like to understand why is that happening. We can, of course, rotate the whole chart, zoom in, zoom out. So like I said, it's a very interactive tool, and we can really dive deep into the data that we try to analyze. So let's look for one of those interesting examples right now. Here in the bottom part of the chart, we see a cluster of images showing number 6. I'm not really good with colors, but those are represented with those darkish pink dots. But suddenly on the left side of that cluster, we see one dot represented by that bright pink color, which is number 8. And yeah, if we zoom in on that image, we can kind of understand why is that happening. The upper loop of 8 is completely on the side, so the rest of the digit kind of like looks like 6. Similarly, at the bottom of the cluster, we have this blue dot that is describing number 0. And yeah, that image also kind of like look like something in between 0 and 6. The loop is unfinished. Here is number 4, for example. So you get the point. This is a very good tool if you would like to understand some certain behaviors of your model that are unwanted, but most likely are related to the data that is used for training or for inference. Sure, it's a little bit more of an art than science, but it's still an awesome tool if you would like to understand more about your data, gain some intuition, look for some patterns, and understand what is important in your particular project. I encourage you to play a little with our demo. You can run it in Google Colab, as I said, and let me know in the comment if you find that useful. As I said a few minutes ago, T-SNE is great, but it's quite slow. So you can alternatively use different algorithm called UMAP to get a similar result. Same as before, let's speed up the process and compare execution times. We can see that the processing finished in 22 seconds. And of course, this kind of benchmark in Google Colab and only with a single example is not really reliable, but I can assure you that on average, UMAP is faster than T-SNE. And similarly as before, we can take our projections that we got from UMAP and display them in 3D space, and maybe even get more intuition about the data set, depends on your interpretation. So for example, here is a cluster of ones, completely separated from other clusters. But for example, here, a little bit below, there are sixes. And we see that there are some individual examples of different digits that are within that cluster, but the reasoning is similar as before. Those are simply very similar to number 6 in the form. Here in the middle, we have something new, 3 clusters of class 8, 3, and 5. So 3 numbers that are visually close to each other. They all have 2 loops, either finished or unfinished, like in case of number 3 and 5. And what is awesome is that UMAP was able to understand that similarity. And even though that those numbers form different clusters, those clusters are really close to each other. MNIST dataset is awesome if you look for simple example to understand the concepts behind T-SNE and UMAP. However, good luck using pixel brightness as your features in real-life scenarios. That idea will simply not work. Typical image taken with your cell phone camera can have at least a million pixels. Each of those pixels is described by 3 values for red, green, and blue. So in total, that gives you at least 3 million individual int values that describe your single image. Looking for any patterns in this amount of data would be like looking for a needle in a haystack, even for those clever algorithms that we are using today. We need a clever way to limit the amount of dimensions even before we will use T-SNE or UMAP, and this is where OpenAI's CLIP model comes into play. It is one of the most important models released in the past few years, and it is foundation to anything that we see right now in computer vision with promptable models. And that's because it was one of the first models to successfully learn computer vision concepts using natural language supervision. As the result, the model can be used in many complicated use cases like zero-shot image classification or image search engines. But interestingly, the model can be also leveraged to generate embeddings that can serve as an input to algorithms like T-SNE or UNet to generate clusters of images with similar content. So let's put that idea into practice. And if you want to learn more, we have a separate video and a blog post about OpenAI's CLIP. Links to those resources are in the description below. Anytime that you upload image into RoboFlow, we actually generate those CLIP embeddings by default. So I can right now pick any dataset at RoboFlow Universe and pull CLIP embeddings for images in that dataset. For this tutorial, I decided to use a dataset of rotten fruits. So inside we have apples and bananas, both fresh and rotten. And we will download information about 500 images. It is not a lot, but it's still a pretty good subset of the whole dataset. What is crucial to remember is that this time we are not using pixel brightness. We are using CLIP embeddings. That information was restructured in a similar way, like in the previous example, into 2D NumPy array and is being used as an input for T-SNE algorithm. And once again, we can visualize the results in 3D space using Plotly. Immediately, we see something strange. So in previous example, we could see easily recognizable separate clusters for each class. Here we have 4 classes, but I would argue something between 6 to 7 clusters. That gives us information that even within a single class, we have some factor that allowed T-SNE to divide images into several groups. And that can be anything, a different lighting condition, different background, different object on the image. So right now we can take a deeper look to try to understand what is going on. First, let's take a look at banana class. It was divided into 3 different clusters. The common factor for the first cluster is that all images have partially black background. This is most likely the result of using augmentation strategy to artificially increase the amount of images in the dataset by rotating the input image by some random angle. On the other hand, we have the second cluster where images were not processed, not rotated, and they are looking like they came from internet. They have this very consistent single color background. There is also the third banana image cluster, where images look like they were taken in the wild. They are placed on a table or on the floor. So in this case, the main differentiator between those three clusters is the background. At the same time, we have a second, very similar class called rotten banana, represented by the purple dots. And what we can see straight away is that this class is underrepresented. We can see rotten banana images close to the first and third cluster, but not close to the second. Apparently, there were no images of rotten bananas on the internet. I don't know what is the reason for that. But in a perfect world, we would see a similar division, both in rotten banana class and in a banana class. And elements coming from both of those classes would be relatively close to each other in our 3D chart. Okay, so I hope that you get the idea on how to use OpenAI's CLIP plus T-SNE to analyze the distribution of classes in your dataset. Now, we can use a very similar analysis to analyze the distribution of images across splits. So, as you are most likely aware, in typical computer vision project, we split our images in 3 subsets: train, test, and validation. For the purpose of that video, you only need to know that images in all of those subsets should come from the same distribution. But at the same time, we really wouldn't like to get those augmented images in our test and validation dataset, because in most cases, they are not actually representative of what we can see in real life. So now let's use similar strategy as before, but to evaluate our dataset splits. Right away, we can see that images coming from test, train, and validation sets are part of every cluster. That leads me to believe that they were most likely picked at random, which is a good thing in most use cases. However, I would argue that adding those augmented images into validation and test set doesn't really make sense. Of course, it all depends on the type of augmentation that we decided to use. Rotating banana image by some random angle doesn't really sound like a problem. However, the dark pixels that were produced as a result of this process caused those images to be clustered in completely different group. Analyzing that chart alone won't give us any concrete conclusions. However, together with training information can be a valuable clue if we want to improve performance of our model. Clustering images and looking for patterns in dataset is not the only use case where we can use embeddings. Another very popular one is deduplication of images. So in other words, looking for similar or close to similar images. It is possible because embedding is basically a vector that describes the image, or word if we talk about NLP use cases, and similar images or similar words will have similar vectors. We can now use trigonometry to analyze those vectors, and in particular, we can calculate the cosine between those vectors to measure their similarity. There are 2 steps that we need to do. The first one is normalization. We need to take every vector that we got from CLIP and normalize it, which essentially means that we need to calculate the magnitude of the vector and then divide the vector by that magnitude. As the result, we get the vector with magnitude of 1, but the same direction as the input vector. Then we can calculate the cosine between those normalized vectors that represent 2 different images. If the cosine value is equal to 1, that means that images are similar. If it's equal to 0, that means that they are orthogonal, which means that they have nothing to do with each other. And if it's equal to -1, that means that they are opposite. What is even cooler is that we can use NumPy to vectorize those calculations, which means that we can compare all images at the same time and significantly speed up the process. As the result, we'll get a square matrix, where every value of that matrix is actually a cosine between 2 vectors describing 2 different images. Now, it would be awesome to visualize those results. However, even with small dataset, and we only have 500 images, it's quite hard to create a plot where you can easily read values of those cosines between individual images. Unless, of course, we once again use Plotly to create interactive chart, where we can just hover on any intersection and display the index of 2 input images as well as the corresponding cosine value. What is even cooler is that we can zoom in on selected part of the plot and inspect cosine values at higher resolution. Now, as a cherry on the cake, I created a small analytics tool that allows us to pick an image and look for n images in our dataset that are the most similar to it. Okay, so let's pick image number 313 and look for, let's say, 5 close duplicates. And yeah, apparently we have a lot of duplicates in our dataset. That's it for today. I hope that you liked the video and find it useful, because I actually plan to create a second video about embeddings where we will explore even more mini projects and try to use embeddings to solve different problems. I already have few ideas on my mind. However, if you have any, feel free to drop them in the comments. I actually look for a little bit of inspiration. And if you used embeddings in your project, let me know how it went. Did you solve the problem that you intended to solve? And in the meantime, like and subscribe to stay up to date with fast-moving computer vision space. We actually try to experiment with any major model that is released. Check our other tutorials about grounding Dino and SAM. And my name was Peter, and I see you next time. Bye.